Sound moves faster in air than in water, yet sonar relies on its sluggishness to map the deep. How can a slow wave reveal hidden worlds? Imagine hearing an object before you see it. What if your ears could chart oceans and earthquakes alike? First, a transducer sends a pressure pulse into the medium. The wave travels until it meets an interface where material properties change. Part of its energy bounces back as an echo. That reflected signal returns to the source, where sensors convert it back into electrical data. By measuring travel time and echo strength, we map distances and surface characteristics, whether it's a ship hull, a fault line, or a concert hall wall. 0.8 A sonar system starts by sending an acoustic pulse out into the medium. The transducer, made from a piezoelectric crystal, receives an electric voltage and vibrates at its resonant frequency. This vibration pushes on the surrounding fluid, creating a pressure wave that travels outward as sound. When the wave encounters an object, part of it reflects back toward the transducer as an echo. The transducer then switches to receive mode, converting the returning pressure changes into electrical signals again. By measuring the time between emission and reception, we calculate how far the object is using the speed of sound. Higher frequency pulses give finer resolution but attenuate faster in water or soil. In practice, sonar arrays use multiple transducers to steer beams and improve detection accuracy. The waveform overlay on the visual shows both the transmitted pulse shape and the reflected echo pattern. Understanding this emission-echo cycle is essential for applications from underwater navigation to seismic surveying. 0.8 Sonar emits a sound pulse that travels through water and reflects off objects. The time between emission and return is called echo delay. Multiplying delay by half the speed of sound gives distance to target. Intensity of the returned signal indicates how much energy was reflected. Strong echoes come from hard, flat surfaces like rock or ship hulls. Weak echoes arise when sound scatters into many directions, such as in soft sediment. By sweeping a sonar beam across the sea floor, a detailed depth chart is built. These acoustic maps reveal underwater features that GPS cannot see because it relies on radio waves. Navigation systems combine GPS position with sonar depth to plot safe routes beneath ice or reefs. Engineers calibrate sonar frequency and beam width to balance resolution against range for specific missions. 0.8 A seismic source emits a burst of energy that travels through the Earth. Primary waves, or P waves, are compressional and move particles in the same direction as travel. Secondary waves, S waves, shear particles perpendicular to motion and arrive after P waves. Because S waves cannot cross fluids, they reveal the presence of liquid layers like the outer core. Surface waves, including Rayleigh and Love modes, travel along the crust and amplify shaking during earthquakes. Controlled explosions release a sudden pressure pulse that generates both P and S waves for exploration. Vibroseis systems use a vibrating truck to impose a continuous frequency sweep on the ground. The induced vibrations produce long-duration waves, allowing detailed imaging of subsurface layers. By recording arrivals at multiple geophones, seismologists calculate velocities and build 3D velocity models. These models help locate hydrocarbons, assess seismic hazards, and design resilient infrastructure. 0.8 Seismic monitoring begins when a fault releases energy and launches waves into the Earth. The fastest of these are P waves. They travel through rock as compressional pulses. Because P waves arrive first, seismographs can detect them before any destructive motion starts. A network of sensors records ground velocity and sends data to a central processor in milliseconds. The processor applies simple algorithms that flag the characteristic P-wave signature against background noise. Once a threshold is crossed, an automated alert is generated and broadcast to emergency services. This warning arrives seconds before the slower S waves, which carry most of the shaking damage, reach the surface. Even a brief lead time allows people to drop, cover, and hold on, reducing injuries. The system's reliability depends on sensor density, data latency, and robust software that can handle false positives. Ongoing calibration ensures that the P-wave detection remains accurate as seismic networks expand worldwide. Pause 0.8 in a concert hall. Sound behaves like waves traveling through air. Engineers shape these waves by adding materials that absorb or reflect them. Absorption panels dampen high-frequency energy and reduce echoes. Diffusers scatter sound evenly to avoid standing waves. Reflection surfaces control how sound returns to the audience. By balancing absorption, diffusion, and reflection, designers achieve a clear reverberation time. Speaker placement is calculated so that each seat receives a uniform sound field. Acoustic modeling uses modal analysis to predict resonant frequencies in the space. Adjustments are made iteratively until the simulated response matches desired criteria. The final design ensures performers and listeners experience balanced, intelligible audio. This acoustic treatment also protects the structure from excessive vibration. Engineers verify results with on-site measurements before finalizing construction. Pause 0.8. The screen splits into two halves. On the left, an autonomous submersible glides beneath a calm sea. It emits pulses that bounce off distant rocks and return as echoes. These echoes are processed to build a real-time map of its surroundings. On the right, a grand concert hall fills with music from a single stage. Engineers use the same wave propagation math to predict how sound will travel inside. By adjusting wall angles and material density, they reduce unwanted reverberation. The result is a clear, balanced tone that reaches every seat evenly. Both systems rely on measuring how waves reflect and interfere in space. Understanding these mechanisms lets designers create safer underwater vehicles and richer listening rooms. This cross-disciplinary insight shows the power of physics in everyday technology. In both realms, precise control over wave behavior is key to success. Pause 0.8. By mastering wave mechanics, we can navigate oceans, predict earthquakes, and craft spaces with perfect sound.